right. Hello and welcome everybody to this next episode of High Performance Delta. Today we're going to be talking about liquid partitioning and what that means for your Delta tables. We're joined today by Cindy Yang and Rahul Mahadev and Jenny Lee, who everybody knows as well from online and from Databricks and from years and years of Spark and Delta stuff and ML Flow and Unity Catalog. Um, I'm really excited about today's session since a lot of people who've been working in data and data engineering for a long time have typically struggled with Hive-Style partitioning and even the recent changes in Z-order clustering. And so I'm going to kick it over to Cindy right now to present why liquid clustering and how this is so revolutionary for our Delta Lake tables in general. So Cindy, if you want to kick it off.
Yeah, we're super excited today to have everyone here where we can share more about liquid clustering and how it's better than partitioning or some of the other traditional techniques. So a bit about ourselves. I'm Cindy. I'm a product manager here at Databricks, working on the Delta team. And together with me today, we have also Rahul, who is a senior software engineer at Databricks as well, working on the Delta team. We both work on liquid clustering at Databricks. So today we'll start off with some quick recap of the existing data layout techniques and its challenges that we might see. And we'll follow it by some detailed walkthrough of how liquid clustering is in action, and then a deep dive into how liquid works under the hood. And finally, we'll also share some adoption numbers on liquid clustering. So before we get into the details of liquid, let me give you a quick background on why we work on liquid clustering in the first place. So given that there are already existing techniques for optimizing your data layout, such as partitioning and Z-ordering. So on the slide, this is a simplified view of some code you might need to be writing to get to a good data layout on your Delta tables. So note that first, when you create your table, you already have to choose what columns to partition by. And on top of partitioning, you might want to cluster by certain other fields. And you need to balance considerations like what is the cardinality of your columns, what is the skew of your data. And naturally, you ask questions like, what columns should I partition by? What should I Z-order by? And you have to choose carefully, because if you choose incorrectly, your queries will actually run super slow. And also, even if you choose correctly, your data might evolve, your query patterns might change, and you might have to redesign your data layout again. And by the way, the simplified code is just one example. In the real world, you might have to be choosing many of these data layouts for many tables all at once. So a quick recap. What is partitioning? So here with the create table partition by syntax, you're dividing your data into different partitions, such that when you query this table, it can skip the specific partition if you filter it by a partitioning column. And another quick recap, what is Z-ordering? So this is a technique for organizing your data such that your related information is stored in the same file. And the overall effect is you no longer have to deal with small file issues. And as you can see, both partitioning and Z-order are good for performance, but requires manual tuning for them to get to optimal performance, and that is not straightforward. For example, when you have to mix partitioning and Z-order, you have to make decisions about which columns to go for partitioning and which columns to go for Z-order. We also have to be careful about the cardinality of a column when choosing partitioning columns, because choosing a high cardinality column will not scale due to a small file problem. And last but not least, if your query pattern changes and you want to change your existing partitioning columns, you have to rewrite the entire table, which is not flexible. So anecdotally, a good friend, Tom, who's an engineer with great OLTP experiences, had their own attempt at using partitioning. So very naturally, they will want to partition by the column they might use the most, which is timestamp in this case. However, very quickly, this table becomes very unusable. And now Tom has to face, large cloud storage bills and extremely slow query performances and high cost due to the small file issues. And Tom quickly realized the mistake and wanted to change the partitioning data layout, but then realized that this is actually not an easy fix. A full table rewrite is needed to change the partitioning strategy. And now let's go through an example that shows the challenges with partitioning. So let's assume we have a table that we decided to partition by date and customer ID based on the query pattern. And assume that we are ingesting data hourly. So these are the data ingested in the first day. As you can see, we have some small files ingested. And again, more data ingested the next day and more data ingested today. Now that we have accumulated so many small files, this could slow down the read performance. So what do? Let's run optimize to compact some of these small files. So here, optimize tries to compact the small files, but it can only do it within each partitioning boundary. So here you can see that it can only do compaction within the dotted boxes. And as a result, you have some partitions with good file sizes, meaning close to the target file sizes, but some of them there's still many partitions with many small files, which can degrade your read performance. And one way to fix this is to partition by week instead of partition by day to make your file sizes bigger. But this requires you writing your entire table, which is not an ideal solution. So as a quick recap, I showed an example of where partitioning cannot solve the small file problem, and you cannot change your partition columns for your query patterns without recreating the table. So to summarize, with partitioning, you have to deal with many issues like small files, data skewed, and slow writes. And sometimes even with z-ordering, even though it can help with performance, it is not incremental and requires manual tuning to decide the best z-ordering columns used with partitioning. And this is not a one-off process. You have to continuously run optimized z-order to maintain a good data layout for your partition z-order table. And this is why we built liquid clustering, which I'm super excited to share more about how Liquid can solve these issues we identified earlier with partitioning and z-order. So to solve the problem I described so far, I want to tell you more about liquid clustering. It is super fast. In fact, with Liquid, write performance could be faster than partitioning and z-order. Rahul will share some results in the later, and it can have similar read performance out of the box, even compared to well-tuned partitioning and z-ordering tables. It is also incremental, meaning that it only clusters the data that needs to be clustered, which leads to lower write amplification and faster clustering time. It is also self-tuning and skew resistant, so you don't have to worry about the cardinality of a column when you choose a clustering column, which is not the case when you pick your partitioning columns. And last but not least, it's super flexible. You can change your clustering columns at any time based on your query pattern needs without rewriting the table. It is super easy to get started and to achieve all these benefits. You simply just have to run cluster by syntax when you create your table. So now let's see how liquid clustering works at a high level. So this is the same data set that I used earlier when I gave you the example of partitioning. So again, how we ingested the table with the same files. And as you can see, there's no restriction on the value of the boundaries anymore. When you cluster this data, liquid clustering can intelligently figure out which files to cluster together, which is shown in the green boxes. And as a result, you get a good clustering quality as well as good file sizes. And as this shows that liquid clustering can solve the small file problem by handling cardinality and data skewness automatically. Now, let me show you a quick example of incremental clustering. In this example, let's assume we ingested a few new files, which are represented as the dark blue boxes. And now let's cluster this table. First, the files in the blue box would not be touched because they are already well clustered. And as you recall, these are the files generated after you clustered the table in the previous slide. And how about this file in this blue box? It is not clustered because the file is already close to the target file size, and liquid clustering figured out that clustering this file will not improve your clustering quality because it already contains a similar range with other files in the same gray region. And what about this file in this blue box? These small files will get clustered to optimize for file sizes. So as a summary, liquid clustering can intelligently decide which files are needed for clustering and cluster the data only if the clustering quality or the file sizes can be improved. And this can reduce write amplification quite significantly, and in return, improves the overall clustering quality as well. Now I'll pass it on to Rahul to tell us more about how Liquid works under the hood.
Thank you, Cindy, for the overview of Liquid. In this section, I'll be going into a little more deeper details about Liquid. So here's what I want to cover. First, let's talk about the prerequisite, which is data skipping. Data skipping is a fundamental technique that is used by Liquid. And then we can go over some of the math behind how we attempt multidimensional clustering. And then we can end with incremental clustering with Z-cubes. So first, refresher on data skipping. So in Delta, when a file is written, we also record the min and max and null count for all the columns of that file. And during reads, we actually use this information to filter out files that don't match the predicates. We can go over a small example to understand this better. We have a table A here, which has a column date, and there are currently 5 files in this table, as you can see. There's file 1 with a min of Jan 1st and a max of Jan 5th. File 2 with min of Jan 6th and a max of Jan 7th, and so on. Assume you have a query as follows. Select star from A where date equal to Jan 8th. So how data skipping helps here is by looking at the predicate, in this case it's Jan 8th, you can filter out a section of the files in the table and only read the files that will contain Jan 8th. So in this example, files 1, 2, 4, and 5 have their min and maxes which don't contain Jan 8th. So we can only go ahead and read file 3, which is bound to contain Jan 8th. So in this exercise, we've shown that with data skipping, you can reduce the amount of data that needs to be read by using this min-max statistics. This is the fundamental building block of Liquid. And now let's take a look at how we can achieve the min and max such that we can skip files during read queries. So before we go into multi-dimensional clustering, let's talk about a simple case first. If you were to just cluster on one dimension, that is, or one column, how would you go about doing it? The answer is actually very simple. So you would just sort by that column, and you would split the sorted data into multiple files based on the target file size. And during reads, you would use the same technique we showed in the last slide, where you would use data skipping to filter out predicates that don't match the range. Now, would the same work for multiple dimensions? The answer is a little complicated because files are in a single dimension, so you can't take multi-dimensional data and just sort them, right? So that's why you need to do multi-dimensional clustering, where you translate the order of multiple dimensions into a single dimension. And we'll see how that works in the next slide. So with Liquid, we use this concept called Hilbert curves, which is actually coming from math. These are a family of space-filling curves. And the other examples of space-filling curves are Z-curve, which is used by Z-order, which is also similar. But Liquid, we use Hilbert. And how we go about filling the space-filling curve is as follows. So if you look at the example on the right here, we have 2 columns, and we have neatly arranged them in a 2-dimensional grid. And we have drawn a curve, which is the Hilbert curve here, to go through all the data, and it provides a single dimensional ordering for all the data here. The sort of rules for filling up the Hilbert curves as follows. So first you divide the space into quadrants, and you first fill up one quadrant completely, like we've done here. And then once you fill up one quadrant, you enter the next quadrant by just taking one step in a given direction. So we enter the next quadrant. And finally, we fill up the complete next quadrant before moving on. So Essentially, if you apply these three rules recursively, you end up with the space filling curve filling up the entire data space here. So that's essentially how we arrive at a single dimensional ordering for our multi-dimensional data. Now let's look at how this actually translates to files in Delta. So each of these boxes now represents a non-overlapping min-max range for the files. And we use range partitioning, which is an operator in Spark, to divide a data frame into multiple parts. And the number of parts here is determined by the table size and the target file size. So basically, if your table size is 10 gigabytes and your target file size is 1 gigabyte, you have 10 bins and 10 files to write out. In the ideal world, you expect completely non-overlapping min-max ranges, but in practice, that may not always be possible because there will be data skew, and depending on the size of the data, uh, this can this can be overlapping as well. So previously, I spoke about Z curves, which is what is used by Z order. And in this slide, I want to go over the difference between the Z curve and Hilbert and why Hilbert is a superior technique. So in the previous slide, we looked at the way the data is laid out and how the curve runs through all the data. And when you divide the entire data space into smaller bins, the unit you're working with is typically the number of points in the data. So if you take the example here, you have the same number of points in the left and the right. The left is representing a Z curve and the right is representing a Hilbert curve. So if you take 6 points on this on the left, you end up with something that spans the entire space of the curve. That would mean you would end up with more overlaps when you write it out as files. On the right, with the Hilbert curve, the same 6 points now only cover half the space. So that means the overlapping range is much smaller with Hilbert compared to Z order. Uh, what that means in practice is you get better clustering quality with Hilbert curve, and this property is known as locality preserving. And that's why we use Hilbert in Liquid. And for the next topic, I wanted to talk about how we achieve incremental clustering with Liquid. With previous techniques like Z-order, every time you run Z-order on a table, what would happen is the entire data had to be rewritten again. So that would be not ideal for cases where you have continuous ETL into the table. But we solve this problem with the help of this concept called Z cubes, where we divide the entire table into smaller zones or regions called Z cubes. And there are two kinds of Z cubes. So a stable Z cube is something that's between 100 and 150 gigs in size. And these are data that will not be rewritten upon when there's new data in the table and you want to recluster. These old stable Z cubes will not be touched. Uh, but we also have partial Z cubes that are between 0 and 100 gigs in size. And when you have new data, the new data is combined with the partial Z cubes, and only the partial Z cube has to be rewritten. So this greatly reduces write amplification and overall reduces both cloud storage costs and compute costs for the optimized operation. And I wanted to go over the cases where the stable Z cube can be rewritten as well. So in situations where you have DML operations like merge, delete, updates, some data that's referenced in a stable Z cube can reduce in size with these operations. And once they go below 100 gigs, they become partial Z cubes. And these become eligible to be rewritten again when you have new data coming in. And it's not there in this slide, but when you have multiple partial Z cubes, they can be combined together as well. And as Cindy mentioned, we had some benchmarks. So we compared Z order and Liquid in performance, and we compared both the write amplification in gigabytes and the total clustering time taken. And in our experience with this, we see that liquid is up to 1.5x faster and cheaper than Z order for the TPCDS 1 terabyte dataset. So to recap, what are the advantages of liquid over Hive-style partitioning? First and foremost, we no longer have the small data file issue, and then we're better at handling skew, as Cindy showed in the example. And writes, if you we're not going to be slower than partitioning at any point for writes. And regarding tuning, you don't need to. It's liquid is at a table level, so with Z order you had to manually keep track of which was the Z ordering column and which partitions were Z ordered. So that's no longer a problem with liquid, and performance is more consistent. And finally, liquid gives you an incremental cost compared to Z order, which was going to be fully rewriting the entire table. Uh, yeah, and I wanted to recap that liquid is easy to use. So if you are starting a new table, you can just create a table and provide the cluster by clause with the columns you're most interested in. And if you have an existing table, you can use alter table to convert the table into a liquid table. And I'm happy to announce that we have a new feature called Optimize Full that can be used to recluster existing data in case that you switch clustering columns and want to have the whole table in a specific way. Uh, yeah, and I'm happy to report some of the usage metrics for Liquid. So these metrics are actually from Databricks customers because we can't really instrument open source for usage, but it's widely adopted and it's being used by over 2,900 users daily. And the largest Liquid table are greater than 2 petabytes. And overall, there's over 100 petabytes of Liquid being written today. And finally, I wanted to end with a call for contribution. Liquid, since it's an open source project, one solution does not fit all. So if there are certain data patterns that might benefit from a different clustering technique, uh, please feel free to contribute. There was one issue along these lines, so that we encourage more issues to come and if you contribute, it might be useful for the whole community as well. Yeah, and thank you. I wanted to hand it over for question and answers.
Awesome. So there's a question that came in from Shantanu. And it was essentially just asking about the computational overhead introduced by liquid clustering. And so how does that contribute to a slowdown in the overall process? And is there a slowdown in the overall process, or is it just depend on how people apply liquid clustering and like liquid optimizations?
A great question, Shantanu. So if you're generally ingesting using like just writing data to the table, you should see no overhead compared to partition tables. In fact, you might also see improvement over partition tables. You would have to run a optimize command, which we also recommend to be run for partition tables and z-order tables as well. So there's no difference in that regard. Uh, with the actual optimize command, this is something typically users set as background operations so that it doesn't affect their general workflow and slow down their other operations. And Delta, as you know, is provides multi-version concurrency control, so you can have these background operations in happen without conflicting with any business transactions.
Awesome. There is a question from Jefferson.
Mm-hmm.
Okay, perfect. Now it's up on the screen as well. So does storing null values have negative impact on liquid clustering?
Yeah, good question, Jefferson. So null, we treat null as the lowest value. For example, if you have null with integers, that would be like considered the lowest. When we order the data, it'll be like the lowest value. If you had it with a string, again, it would be the lowest value. So depending on the type, null would just mean it's the lowest value. So if you have some nulls in your table and you cluster by the table, that means the nulls are all co-located together.
All right. So we have, apologize, I don't know if my video is kind of skipping, but hopefully the audio is coming through as well. There's another question that kind of comes up a lot. And so for people who currently have tables that are partitioned with Hive-style partitioning, what does the path look like to utilizing liquid clustering? And what does that process look like in the case where you already do have partition columns in place?
Yeah, Cindy, do you want to take that?
Yeah. So in terms of, I currently have a table that is partitioned and I'm looking to adopt liquid clustering. Well, what the pattern we see is that customers can do a C task from the old table or create a table in place by running a replace table command. And here you can define the clustering columns as it is. We do recommend not, sometimes the partition columns can be good enough for the liquid clustering columns, but we do recommend, for example, if you used to have, you have to have generated columns on top of your timestamp, you don't have to worry about the cardinality anymore. So I would recommend, do the seed has or replace table as the migration strategy. And in terms of choosing the columns, I would recommend, don't worry about cardinality. Think about what you query the most when you run queries on this table, and use that as your new clustering columns.
Perfect. And a follow-up example for that too, in a lot of cases where people are taking timestamp millisecond values and then basically projecting them as dates, it's to go back to timestamps for this, for better clustering, right? Awesome. Okay, so we have a question from Posha. And so for the technique, all right, so I don't know exactly what this is asking. So does it ensure the clustering technique is still optimal as addition of new data? So do you want to talk a little bit more about like the incremental clustering and what that means as well? I think that this question is asking more about the incremental clustering.
Yeah. So what happens is if you have new data, and I went over like the partial z cubes in my slides. So for the partial z cubes and the new data are taken together, clustered using the same Hilbert clustering technique, and they're written out. So the whole table need not be rewritten when you have new data. Only the partial z cube and the new data has to be rewritten. So in practice, if you have, let's say, 100 terabyte table, only 100 gigs of up to 100 gigs of partial z cubes, and the new data that you ingested, depending on how much you ingested, has to be rewritten.
Awesome. And we also have a question from Avishek. So the question is like, okay, perfect. What's the size of the table that benefit from liquid clustering?
Yeah, good question. So size of the table actually does not matter. The real parameter that matters here is the size of the files. So if you have, let's say, one gig file sizes as your target, and you have, let's say, just two files, then if you liquid cluster on that, you're only skipping between like two files. You're reading either one file or two files. So there's not much there, right? But imagine you had 1,000 files of 1 gig in size. In that case, when you have like point queries, you're reading one file and skipping 999 files. So that would be effective. So the way I try to look at this is try to see how much selectivity I have and what my file sizes are going to be, and based on that, make a decision to use liquid or not. But if you're going with one gig of file size, I would say around 100 gigs is when you start actually seeing real benefits.
Perfect. Okay, and so another thing just came in from LinkedIn as well, from Nitin. And so is there a situation where just regular partitioning would be better than liquid partitioning?
Yeah. So partitioning, if you've tuned it well, like for example, uh, in the example that Cindy took, there was timestamp in the first example. In that case, partitioning would not be good. But let's say you just had date and you're only querying by date, and that was fine with you, and it you don't plan the data patterns to change. In that case, partitioning is actually good enough, and you don't need to really upgrade. But if you have like changes to the data distribution, or if you want to change the columns. So there was one user I was speaking to who had date, and they were happy with date, but they they had a lot of data coming in, so they wanted to like have better data skipping. So they wanted to go from date to date and hour. So that would be a case where if you foresee that happening to your tables, that would be a good opportunity for Liquid, in my opinion.
Awesome. Let's see. So we have there's no other questions coming in right now as well. But if you think about like kind of like the trajectory of where things are going with Liquid, and also kind of the call to action to bring like different like clustering algorithms into Liquid, what do you see like? How do you see like the benefits kind of changing as we're kind of preparing for kind of more like agentic workloads and things like that? Do you see a strong kind of correlation between the way that our data can change to adapt to things like more on demand? What are things that kind of like excite you within like the realm of like liquid clustering?
Yeah, I think there was a statistic I saw somewhere that the amount of data being generated every year uh, increases exponentially, or something like that. Like, so every year there's more and more data, and having techniques like Liquid, where which allows you to read only the subset of data based on the query predicates, is very important going forward. And every organization is gathering more and more data from their processes. So techniques like data skipping are going to be more important as time goes on. Cindy, I don't know if you wanted to add something.
Yeah, adding on to that, I think one trend we also see is that more and more data practitioners, they can, with Liquid, they can just think about what query pattern they have and choose the clustering columns on that. Again, you don't have to think about, what is the data layout strategy, what's happening under the hood. Do I have, problems like small files? Like the trend here is we want more and more people to be able to, just set up their table, start running queries, and not have to worry about any of the configurations you might have to do with the old techniques like partitioning and z-order. So that's why we're really excited about the simplicity side of things as well for liquid clustering.
Awesome. Let's see. So cool. Here we go. I think we did answer kind of a version of this before. So Cindy, is it okay if I just recap for this one? So for this one, if you already have a table that either if it doesn't have any partitioning yet, you can alter the table to add clustering. If it already has traditional Hive-style partitions, then you can overwrite it and with like replace where. Is that correct? My overview of that over there for that. So we still have to overwrite the table to be able to rewrite it, right? To remove the old Hive-style partitions. Otherwise, we get locked back into the current layout of the table. So in the absence of partitions, it's easier to add liquid partitioning. Where you have Hive-style partitions, you have to overwrite the table anyways. Hopefully that's a good answer. Yeah, Cindy or Rahul, do you have an answer for this one for how we integrate database metadata like Liquid-based to manage versioning and history for tables? So we already have the transaction log in Delta. So there'd be a benefit to having external management. I don't know, Kumar, if you want to, if you could expand upon that question, or we could just follow up offline as well for that one. I think it needs a little bit more detail. Okay, so new question coming in from Jefferson. How frequently do we recommend running optimize? Fact tables clustered in high cardinality columns. Fact tables updated every 30 minutes.
Yeah, I think the rule of thumb here is how much the updates are. For example, if the updates are going to be like less than 1% of your table size, in that case, you probably don't need to run an optimize every 30 minutes. So what I have seen in practice that works well is someone's using, let's say, a streaming ingestion like for each batch. They sort of run optimize every 10 batches or so. So in your case, if there's a batch every 30 minutes, uh, like having an optimized run after 10 batches would be something that's optimal. But then again, this really depends on how much data that's coming in that 30 minutes. If it's like 10% of the table, then I would recommend running optimize right away. But if it's smaller streaming ingestions, then you probably want to hold off and run them all uh, at a at a coarser duration. 500 million rows. Okay. Yeah, it depends on the table sizes rather than the rows, I would say.
All right, we have the question from Devesh. So it's a kind of an opinion, right? So liquid clustering seems like a file pruning technique, but how to implement it? I mean, in this case, right, it comes for free. It's part of open source Delta, so you just have to turn it on. If you wanted to implement it, then research into Hilbert curves makes sense, and then taking a look at the open source Delta, you can take a look at how Z cubes work as a way of kind of diving into that. So I'm not sure, Divesh, if you were looking to kind of extend liquid clustering, and if so, there's kind of the call to action before. If there's new techniques you want to bring to the table, you could contribute as well. All right. Let's see. Looks like the questions are keep coming in. So Cindy or Rahul, do you want to talk more about like transaction log and where additional metadata is being stored as well?
Yeah, the additional metadata is stored. So, in just to recap, in the Delta transactional log, each file is represented with an action called the add file. So, add file references one Parquet file, and with that, we also store. We can store like tags. There's a map object inside that can store any information we like. So we use the same map to store tags on what Z cube this belongs to and whether it belongs to Z cube at all or not. All of this is in the add file tags.
Awesome. And for people who are curious about what that looks like as well, they can take a look at the Delta protocol, which is available also in under delta.io/delta. All right. Are there any like? So we're almost at the hour, and so would there ever be like? So the questions come up of when to use kind of traditional partitioning and if that makes sense to continue to do that in a world where we have something like liquid clustering. Is there ever a reason why you would say don't use liquid clustering? You know, in the case, like one thing that I can think of is with essentially tables that are being overwritten completely, where there might not be a reason to continuously try and cluster, given that you're going to be overwriting that table, you know, say it's a daily. What would be a reason to just skip liquid clustering in general?
Yeah, I think what the example you gave is really good. Where if the table is getting rewritten completely daily, or there could be cases where you don't have predicates on your queries, right? I have a lot of tables, and some of the more dimension tables, I read them completely. I don't have any predicates on them. In that case, I don't bother with either partitioning or liquid. I just read any. If it's like a few rows, then I just end up reading the entire table anyways. Uh, yeah, those are some cases where it doesn't matter.
Perfect. Yeah, I mean that makes a ton of sense. I think there was like the recommendation prior to liquid where it's like if your table's less than a terabyte, really don't think too hard about how you're partitioning. It's going to be fast enough. That was like the recommendation for things running like inside of Databricks, where it's fairly fast to go and read, and then just kind of lean on the stats columns themselves. We talked also a little bit more about stats as well. we just had a question come in, so I can just I'll just recap real quick. So stats are used for file skipping, and stats are also used to be able to optimize like our inclusion within the Hilbert curves themselves as well. Are there any recommendations you have for customers who need to have, like, who want to understand more about like when would a string ever matter, and should we just stay away from strings with our stats columns for Liquid? Are there any kind of rules to, is it better to stick with numeric types?
Yeah, great question. If you have something that resembles a date, I would recommend just using the date itself. It's going to be a more efficient data type. Uh, if you have very large strings, one nuance we have with Delta is we only collect statistics for the first 32 characters of that string. So if, for example, you're going to store hundreds of words, in that case, you probably are not going to get a lot of good data skipping from it. Data skipping is meant to be more useful for other cases where you are searching for particular group, particular type, rather than like needle in the haystack string search. There are other tools for that. Uh, but if you have a string column, let's say something that categorizes a group and is within like 32 characters in size, then I think you're fine with using string as well.
Great. All right, and then I think for the last question we'll take right now. So for Liquid Cluster, so this is from Avandro. So just checking if I got it correctly for Liquid Cluster. I don't need to take into account the cardinality of whether the data is skewed or whether the column is used in a query. Is that right? Who would like to take this one?
Yeah, I can take this one. So if I understood the question correctly, it's asking if I should I care about cardinality. The answer is no. That was the goal of Liquid, is regardless of what your cardinality is, we will support you. You don't have to worry about that. But the second part of the question is, do you care if the column is used in a query? I think that is important. If you pick a clustering column that you don't plan to use in your query, then it's not going to be very useful. Um, and if you have like two columns and you're using one of them heavily in your queries, but you cluster on the other one, then you're no good with Liquid. So we would recommend picking the columns you plan to query on the most. Also with Liquid, as Cindy spoke during her presentation, you can run alter table to change the clustering columns as your patterns evolve. So that gives you the flexibility to not worry about the second part as much compared to, let's say, partitioning, where once you make the decision, you're stuck with it forever.
Do you want to dive a little bit more into that? So if you think about like dynamically changing the cluster columns, what does it look like when you're doing like a longer query back across the entire table?
Yeah, if you're if you have a query that doesn't have any predicates or has a predicate on, let's say, like on a column that isn't clustered. So I went through the example of data skipping using min and maxes. So in that case, if it's not clustered by that column, the min and max will be the entire range. For example, if it's a date column, it could be like Jan 1st to Jan 31st. Min is Jan 1st and max is Jan 31st. And it would be that way for all the files. So data skipping is going to run and it'll say that, hey, you need to read all the files to answer your query. So you're doing more IO to the cloud to read those files. And it's going to take longer because there's more work to do. So yeah, if you didn't have any sort of data skipping, long story short, your queries are going to be much slower and much more expensive.
Awesome. And then this will be the official last one we have for this first session on liquid clustering. So does liquid clustering work with the SQL endpoints? This is going to be probably specific to Databricks and probably DB SQL for the SQL endpoints. And Cindy, do you want to take the final question?
Yep. This works with SQL endpoints for sure. Yeah.
Awesome. Then that is going to be a wrap on Beyond Partitioning. And Avishek, I saw your question just come in. We can follow up with this after the fact as well. So we'll just close down the webinar. So thank you so much, Rahul. So thank you so much, Cindy, for coming on board. And thank you to the audience for dealing with some of the technical difficulties as we're getting started. And we'll look forward to seeing you again soon. So thank you, everyone.